As a final topic of today, let's consider unsymmetric loading of thin world members. So before begin, let's compare the two cross-section, symmetric cross-section and unsymmetric cross-section. So for the unsymmetric cross-section, it's easy. We can apply for normal stress and shear stress equations without any difficulty following the equations we derived in previous lectures. Regarding the unsymmetric loading, unfortunately, even though we can apply the normal stress equation which we already have done in previous lectures, but we cannot apply the expression for shearing stress. And why we cannot apply this? It is because of the twisting. Even though I cannot tell you the full mathematical detail about the twisting and why we cannot apply this equation, the physical reality is following. So for the symmetric cross-section, there is no twisting, but for the unsymmetric cross-section, there is a twisting of this beam, and because of this twisting, which is related to the shearing stress, we cannot apply this expression as it is. Actually, this expression only holds if there is no twist, as I told you in previous video of today's lecture. So because the full mathematical description is out of scope of ME tutorial, what you're gonna do instead is following. We'll just consider the loading condition under which no twist occurs. Okay, so how we can do that? Our strategy is following. Suppose that the shear force V is applied such that the beam does not twist, then we can apply this equation. Okay, in that case, we can draw and we can obtain the distribution of shearing stress and Q distribution. Out of this distribution, because this infinitesimal force at each infinitesimal area is Q multiplied by ds, you can obtain the force at the top, and you can obtain force at the bottom, and you can obtain the force at the web area, the vertical wall area. Now what you can realize here is this is the case when there is no twisting, and we can think about a statically equivalent problem. For statically equilibrium problem, you have to have same force in x direction, same force in y direction, and you have to have same torque. Let's say that the torque is in this direction. So if you look at the original problem, the summation in force in x direction is 0, summation in y direction force is v, and the torque is counterclockwise torque. To make a statically equivalent problem with only one v, we can think about following. So if you have this problem, no fx, right, and there is fy, which is the same as the original problem, and you have torque, and regarding the torque equilibrium, you have to consider center of the torque. Let's consider the origin of torque here and origin of torque here. So regarding the torque, there is no torque due to this v, but there is torque due to f here and f prime here, and the distance to the reference point is h/2 here, h/2. So the counterclockwise torque for the original problem is 2 times f times h/2, and the torque for the statically equivalent problem is v times e. Okay, so by recognizing the equality between left hand side and right hand side, you see by cancelling 2, fh equals to be va. If you consider e as location as b over fh, or in other words, if you apply your force e distance away from this center, then you can say that there would be no twist, such that you can use the equation vq over it. We call this position as shear center, and typically the problem asks you to obtain the shear center. After obtaining the shear center, by using this equation to obtain the shear stress distribution. Okay, so let's try to solve one example problem based on this primary discussion.